And then, and before, let me attract your attention. Here is the schedule for the next Friday, right? So it is based on your votes, and in vast majority, I was able to match your first choice. The only situation when it is opposite to your votes is number 1 and number 3. So Joshua wanted to do number 1 and 3 as second choice, and May mentioned number 1 as her only choice. But other than that, everywhere, like Nate, movies, Sibel, variables, Wyatt, programming, Lola kind of agreed to teach us how to make figures. Joe selected to do eigenvalue, and they're yours. Adam wanted to do matrices. It's his. Joshua wanted both complex numbers and vectors. So vectors, Joshua, I hope it is acceptable. Allison wanted to do differentiation and integration as number 1, and May should do number 1. So 4 minutes presentations, submit slides by Thursday midnight. And I intend to share whatever was done in previous years. So it's not for literally copy pasting, but you can get inspiration and get an idea what to show. If I forget to send it, I appreciate reminders. So I plan to send it maybe tonight. Okay. So here are the points. Total number of points for homework 2 should be 100. Does everyone has something to write with? Yeah. I have a couple of color pens. If you need, feel free to take. Like you can do green, red, purple. Orange. Okay, so 40 for first, 40 for last, 20 for second. If you are at home, just open your homework. So the practicing of the little image that you may enjoy. If one last time on the lab we did reproduce the number 3. Here is how one can reproduce problem number 1. So if one adds together several trigonometric functions, you see this images how they reproduce the step function, but we need to get it through the math. So let's go step by step. So term A0, if one is getting that it is, if one identifies that one needs to integrate not the whole space, but only one period, give 10 points. If one gets right answer for 1/2 for A0 term, give 5 points. And try to be generous and give benefit of the doubt to those you're grading. Now for A1, the natural thing is to integrate over the first half of the period, and then one changes integration of variable, makes integration of cosine and plugs in the values, and the answer is 0. So if all A terms are zeros, give 10 points more. Then for B1, one also needs to integrate only over the first half period, and then one just do regular thing, changing integration of variable, integral of sine, and then plugging in the cosine pi, cosine 0, getting 1/pi. So if answer is correct for B1, give another 5 points. And then if there is difference for even and odd B terms, give so it should be 1 over n, 1 over Pn, where n is odd, then given another 5 points. And another way to grade, if you see the complete answer, you can give 100% credit, no matter how it is obtained. So the answer is either set of the coefficients or function is equal 1/2 plus 1 over pi sine 2 pi x over L, 1 over 3 pi sine 6 pi x over L, right? So by adding together these three functions, if one plugs it into MATLAB, one should get a function that will be similarly reproducing this set of steps. Okay, problem number 2. Just check if the right things are plugged in. So if Hamiltonian is in differential form as a second derivative, 5 points. If there is a plane wave with or without normalization, 5 points. And if there is an attempt to plug in the plane wave function into Schrödinger equation to practice second derivative, and if one arrives to this energy as wave vector squared Planck constant square over 2 masses, then give full credit. So for the problem number 3, if you do see an attempt to identify full square, immediately give 15 points, even if the rest is wrong. Just credit for a healthy direction of thinking. If the attempt to identify full square and put factor outside was successful, give another 5 points. If you see the change of a variable, so it will be e to the minus y squared. So such variables in which under integral you have just Gaussian function without any factors, another 5 points. And if the one whom you are grading identifies that Gaussian integral is square root of pi, give another 5 points. It would be okay to give full credit if you see the right answer, but if you want to be really, how to say, sharp grader, and you see only the last answer without steps, you can withdraw a little bit or mark a reprimand comment like, you didn't prove that this is the right answer. It was already shown in the lecture. I want to see the derivations, but just withdraw a little bit, only as a little note. Not we shouldn't ruin careers of each other and let grades to be reasonable. Okay. Do you need more minutes?
Maybe a minute or two.
Okay. Yeah, and when you're done, just add together all points and write it at the front page. And let me bring the yeah, with total points. I may keep processing. I may try to do online grading next time, but it's much more efficient in person by pen and paper. Online takes longer time and it's a big mess. Done?
Yeah.
Oh, thank you. Oh, good. Yeah.
Did you see for mine? I did like.
Huh?
I did one. I did problem one last. I'm telling Joe. I was like, that one's harder. So
What you're disclosing each other who was grading whom and requesting a free beer? No, we shouldn't practice corruption. Yeah, many thanks. Excellent, thank you. So I strongly appreciate. Let me make a note. Who was graders for possible for the reward. And maybe if I decide to practice similar thing next time, I'll try to make an experiment of online grading, but you may not like it. In person, it's just better. It's easier to organize. Okay, those who were online, please send me your grades, not as a number, but as your comments to your own work. So it was like an attempt to correct. Okay. So next homework, I wasn't able to correct this number, but today is 24th, 25th, 26th, 27th, 28th, 29th. So Wednesday, September 29th, right? So that you can slowly complete it, and it would make sense to finish it before presentation, so that on the night before presentation you don't feel pressure from the homework. There was an email, I think, from Ellison. So Ellison, here is an announcement of the homework. It is included into a couple of slides of the lecture notes. If anyone wants, I can cut them and send as a separate email, as a separate document. So you were going over this assignment last time, right? So just practice simplest form of commutation. Extract something from the lecture note and in your own language with comments. Find normalization, find expectation value. The answer should be x naught if the normalization is done correctly. Reproduce how the product of width goes with time, and match the boundary condition between this function and these two conditions. So when x equals either 0 or L, function must turn into 0. Find which coefficients A, B, alpha, and beta will match this stuff. and if you've been up for 100%, this one is only if you have energy. It's if you take integrals every day, it may be easy. If you don't, it may take you like more than an hour. If no, and it is not mandatory. So here is the last slide that I plan to arrive to. So by now we did practice 3 ways to predict future: the evolution operator, the finite differences like evolution for infinitesimal time by multiplying wave functions by 1 minus I over h bar Hamiltonian times delta t, right? And the third way is to expand the initial state in terms of all eigenfunctions, find expansion coefficients, and then construct the wave function of the future as a superposition of eigenfunctions times exponentials, each of which accumulates phase with appropriate pace, right? So what we did for the homework. There is a third way to predict future, which is on one aspect is much better, on another is much worse, but we shouldn't limit ourselves to only 3 things. We need to have an arsenal, a toolbox that can help to any circumstances. And this third way to predict future is not as general as the previous one. So previous 3 were giving us wave function of the future, which contains information about everything which will happen. The one here deals only with a result of observation, the measurements. If we know for sure which observable we are going to look at, there is a way to predict how the outcome of experiment will change with time. So it is more practical. It's maybe the only thing that one needs to interpret results of experiments or predict outcome of experiment. But philosophically, it's a little poor because it doesn't show everything. It focuses only on one thing. And mathematically, this way to predict future can be much cheaper. So much less operations and much higher chance of success. Especially half a century ago when people didn't practice computers, when mathematical expense of a problem was a big problem. And now it's used as well. So we are going to practice it for predicting position of the center of the wave packet. We are going to prove that it will be moving on a straight line with x equals x naught minus or whatever plus initial momentum over mass, p naught over mass times t, right? Does it click? So same as in first law of Newton. If the particle doesn't experience any force, it continues to move on a straight line with constant velocity. So we are going to get it out of this equation by, instead of a, we will plug x. And in order to find its motion over time, one would need initial conditions. So this will be a short-term benefit. Long-term benefit is a chance to predict outcome of measurement for anything, for any variable in the future. And sometimes focusing on one observable is more efficient. So you have broader range of toolbox, and we will select in later in the course which one is more or less applicable for a certain problem. So when we met here last time, we were agreeing that both notations are okay. So if the wave function is without conjugation and Hamiltonian is without Hermitian conjugation, this differential operator acts from left to right, as we used to think all our life until last Wednesday, right? If there is a Hermitian conjugation appearing in there, then we should think that operator acts from right to the left. So we are going to use this paradigm to go forward. So in case we do have a regular Schrödinger equation, right? Time-dependent Schrödinger equation. We will have the solution proportional to evolution operator, right? Which can be interpreted as this factor, so minus I over h bar total energy operator times t. So if you propagate forward in time, time increases, we propagate. If we practice time-dependent Schrödinger equation for the conjugated wave function, we swap the order of wave function and differential operator, and we swap the sign in front of minus I, right? So if we want to find how this conjugated wave function evolves forwards in time, it can be cast in form of evolution operator, but since Hermitian conjugation of Hamiltonian doesn't change it, it will be still the Hamiltonian, but there will be plus sign instead of minus, right? Now, how can we interpret it? So we can multiply it by -1 here, so that it will be equal to stuff up front. And to compensate it, we must to multiply t by -1. So it will be the same propagation as before, minus I over h bar h. And here also minus I over h bar h, but in the negative direction. So propagating backwards in time. So it doesn't, we're not doing actual time machine. It's just an abstract concept, but one can think of that conjugated wave function propagates backwards in time, or just its interpretation of flip of the sign. Okay. So this is the key slide of today's meeting. If we have predicted wave function by either one of the first three methods, we can always find expectation value of an observable by making this bridge from abstract wave function to expectation value, right? But now I would like to formulate the following question. Is it possible to predict outcome of measurement without knowledge of a wave function? Are there any tricks? Because by now, and generally in this course, we are speaking only about one-dimensional wave functions just to make our life easier, but actual molecules are three-dimensional. And then three independent variables, it makes things harder. And if you have more than one electron, each electron has three Cartesian projections. So two electrons will be 6-dimensional wave functions, and actual like atoms and molecules have like hundreds of electrons, which means wave functions that depends on if there are 100 electrons, it will be 300 independent coordinates. So predicting wave function doesn't look always a practical way to work. So therefore, we are coming to a question: if it is possible to predict the result without knowledge of the wave function, is there any trick to avoid it? And there is an idea to assume that we know initial value of the observable and then find observable is a number. It's not a vector, it's not a function, it's not an operator. So it's easy to deal with result of measurement because it is not like real number that you can hold in hands. Can we predict how it will change over time? Can we just, as a mathematical experiment, apply the derivative, time derivative, to the left and right side of this equation, and just check if you get any healthy differential equation that we can solve? Make sense? So if everyone accepts this statement, then we can try to apply the derivative to this product of three objects, right? And it will be not wrong to swap the order of integration and differentiation because they apply to different variables, right? Now, how do we take derivative of a product? Can you teach me and give the name of the rule or product rule, and how do you verbalize it?
First times the second plus the first times the second.
Everyone agrees? Okay, so and if it is not two product but product of three, it will be the same. To one function we apply derivative and other two functions stay unchanged, right? So apply derivative to the first function, other two stay unchanged. Apply derivative to the second function, other two stay unchanged. Apply derivative to the third function, others stay unchanged. What we should focus at that there is a little star, and previously we were preparing ourselves to deal with this conjugated wave function. So generally all three terms must be there, but in many basic exercises it's okay to assume that operator doesn't change over time and this term will be zero. When we cannot do so, we cannot do so if during the measurement, I'm giving an example, I'm not giving general answer, but for example, if during the measurement of some properties of molecule, it is being irradiated by laser. Laser corresponds to changing electric field with high frequency, and then the operators also change over time. And then there should be additional term. But if we have a static situation, if you have our molecule, a piece of material that you want to characterize and put it in some instrument, then one can assume this is not good. Now, we do have two types of derivative. One is derivative of wave function, regular wave function. Another is derivative of wave function with star. What do you think about it? What will be? Well, you all have notes, but can you guess what will be on the next slide? what is the connection to a previous exercise that we did. Yes, exactly. So can you?
Basically just taking everything we learned last lecture about the wave packets and plugging it back into this equation.
Okay, yeah, thank you. So Joy is telling that we are going to plug in something, right? But specifically, what are we going to plug in? So we are going to replace these two derivatives by something. What can we replace it with? Just make some crazy guess.
No idea.
What is equal to time derivative of wave function? Like which equations did you study? What is the main equation of this course?
The Schrodinger equation.
How does Schrodinger equation deals with derivative of the wave function?
There's the Hamiltonian and the imaginary number over Planck's constant, but is
Exactly. Thank you. It's exactly what we need. We can probably replace the derivative with the stuff that you prompted. Wait. Any hints what we should do?
Well, we already said plug in the other side of the Schrodinger equation.
Okay, perfect.
Right.
Yep. It is what is needed. And why are we doing it? Because we hope to bring this equation into the shape where one would be able to solve to find the propagation. One would be able to convolute everything here into something that one can process forward without knowledge of the wave function. So we want to get rid of the explicit wave function, if possible. And right now it looks like boring words, but very soon, in a few minutes, I hope to convert you on the side of this equation. So we're going to plug in a regular Schrodinger equation minus IH bar Hamiltonian times psi here, and the stuff with for the conjugated wave function that propagates backwards in time, where we swap the order of wave function in Hamiltonian, right? So the swapping of this order is would be key factor in the very near future. So regular Schrodinger equation. Thank you, Nate, for memorizing it and being able to reproduce it by memory. Right? And the Schrodinger equation for travelers in time, those who go backwards in time. So we are replacing time derivative by this wave function and Hamiltonian, and we get rid of the time derivative, right? So as a result, you have time derivative on the left and no time derivative on the right. That's what would be the next step? The next step, let me attract your attention and follow what will be the sequence of things in this big bracket. So for each term, you have wave function conjugated, then Hamiltonian, and then operator, and then wave function without conjugation, right? So this stuff will go here, this stuff will go here, and we count first psi star, second Hamiltonian, third A, fourth psi, right? Here you have psi star A, then you have Hamiltonian, and then you have psi, right? Okay. this model of the operating system and cell phone will beep until you admit that the message is received. So it will continue beeping when we use one message. So there are 4 objects, 4 here, 4 there. Each of them starts with psi star. Each of them ends with psi without star. Right? And in the center, you have combination of Hamiltonian operator, but they are coming in slightly different order. But other than that, we have psi star psi, psi star psi, and something in between, right? So I'm just keeping an intrigue, although everything we do can be squeezed through in 5 minutes. If I jump backwards in here, so let me attract your attention to this equation for expectation value. You have psi star, some operator, and then psi, right? So whatever is in the middle is our operator. And then we process stuff from here into there. But now we can put not one operator, but like 2. For example, like HA, right? In the same definition. And then it will generate us expectation value of HA. There is no one forbids us to find expectation value, not of one operator, but of product of operators, right? The definitions is not damaged by this trick, or even 3 operator. Yes. I hope everyone online shows thumb up. It's just a little easier to interact in the class, but maybe in the future lectures, I'll try to communicate to everyone. Okay. So, as we were discussing, the top part includes 2 terms, each of which has 4 factors: psi star and psi, psi star and psi, and combination of Hamiltonian and operator, which we put letter A in general, but in the near future we will place X instead of A. So all this stuff is enclosed into brackets and integrated over space, which means it's like a definition of expectation value, right? I can even put psi star outside of bracket here, psi without star outside of bracket here, and then tell it will be expectation value of the Haha operator, or more exactly HA minus AH, right? And we are very close to the end. So change in time of the expectation value of the operator A will be equal to the expectation value of the combined operator of products between our main interest A and energy operator. Make sense? Basically, we are done. Now I just want to wrap it up in better shape. And on Monday, we will practice the application of to free electron in space. So there is a notation which is designed by lazy people. No, because of the conjugation, the sign is different, right? So in one term it is minus, in another is plus. So we have subtraction, and the order of operators is different. The question number 1 in your forthcoming homework deals with swapping the order of operators in the very simple situation. Can one swap the order of derivative and operator of position, right? You don't need to memorize it, but I'm re-announcing it. So by swapping order of position of two operators, one can get different results, and one can prove it versus some basic differentiation rules. So here, this experience and this understanding that it's not, we need to pay price for swapping order of operators is connected to the stuff we do here. So in fact, it's like two operators. If it would be not operators, but regular numbers, like 1 times 2 minus 2 minus 2 times 1 will be 0, right? But here, if those are operators or matrices, it is not always true. The order does matter. And the main idea that change in time of the operator's expectation value depends on how strongly this difference is. Can you prompt me or suggest any name for this property? How strongly product of operator and Hamiltonian in direct and reverse order differ from each other? Let's design names. Let's design names for how do you call this ability of operators to give non-zero value if you swap the order?
They're like proportional or something.
Okay, proportional. Let's try. Maybe you'll come with better name. So proportional. Any other words? Let me keep the circle and make an interview and. Okay, it is an important feature that product of two operators in forward and reverse order is not equal. Can we design a word in one word to say what is this property? The ability of operators in different order being not equal to the product in different order is not equal to each other. Just try anything. Like swapping property.
No.
Okay.
Swapping property.
Okay, yeah, thank you. Nate, would you like to try your work in designing names? No, just explain what you see. Like weird multiplication.
Weird multiplication swap property.
Okay, yeah,
That's
thank you, Nate. So it's all correct and not far from what is used in the community. So I'm not a big supporter of the name that actual name that is used, but the word is to commute. Yeah, or commutation. It looks very strange for me. What the first impression of this word as a just regular person in the culture, not in the math. I see connection with Mark Twain, Yankee by the Court of King Arthur. When he did you watch the movie or read the book? It's like a comedy of 100 years old about the time machine of the American who worked as the engineer on gun factory, traveled like more than 1,000 years back, and became influential by designing guns between medieval knights. But he was also pushed to learn their traditions, and Today there are much more fun stories, but 100 years ago it was fun, and even now one can read it. So he also established a telephone station, not cell phones. It was not available, but cell phones, and the telephone connection 100 or even more years ago, there were no machines that connect numbers between each other. The, so to say, ancient telephones did have a commutation station, or commutation means connecting. And instead of robot that connects you to a right number, now you dial a number and it's immediately connected. But like more than 100 years ago, there were like postman or telephone lady who sits in front of a big panel with numbered numbers of the people you want to talk to. So she has a wire, and you take, please connect me to the number blah blah blah, and she like looks for the number and connects. And in my mind, this was commutation. How does it connect to the word used here? I don't understand, but it is what people are using. So if two operators are swapped by their order, it's property of commutation. But I remember your words, like your attempts, like proportional swapping, but you've thought like swapping order, that also swapping is probably would be the better word. And there is a notation. If one has two operators like H, A minus AH, it's 1, 2, 3, 4, 5 symbols. One can replace it with also 5 symbols, but it will be more compact. So one writes it as H, comma, A. So when two operators are swapped, there is a common notation of putting them in the rectangular brackets, putting comma between them, and call it a commutation or commutation product, because it is a product, but it's swapped. And if this product will give 0, then one tells that these two operators commute. If it will be non-zero, they do not commute. And we can see, oh, we are over time. If they commute, if one gets 0, then the result will be that the expectation value will not change over time. Time derivative is 0. So it's important. And here's the final slide. So based on this equation, one can plug in any operator, for example, position operator. And then since it is differential operator, this is also can be differential operator. You just practice this commutation, solve the stuff, and then you get regular differential equations, no wave functions, only this function of observable as function of time. And you see, even with million dimensions wave function, it will be just one-dimensional function of time. So there are situations when it is comfortable. So if they commute, result of measurement doesn't change over time. Thank you for your patience and attention. Have a nice weekend. Looking forward to see you on Monday, and please expect some examples of the slides about MATLAB from me. Everyone is welcome to disconnect and depart, and I will stay here just in case questions appear.